Hi, I'm Nishka. Welcome to the video presentation of my final year project, an Affective BCI system with music in an immersive environment. To give context for my project, we must take note that mood disorders are a class of serious mental illness which leave patients' general emotional state inconsistent with their circumstances to such an extent that it actually interferes with their ability to function. The World Health Organization's Global Health Report in 2017 estimated that of the world's population, 4.4% suffer from depression, while 3.6% suffer from anxiety disorders. These percentages account for millions of people worldwide. In recent times, virtual reality and music therapy have started to play a larger role in mental health contexts. Music therapy is an evidence-based therapy technique which employs listening to or playing music as a tool in reducing stress or improving mood. Evidence suggests that individually, both VR and music therapy are effective in improving mood states, as well as alleviating stress and anxiety in patients. The aim of this project is to collect electroencephalography or EEG data from participants in response to generated music stimuli in a VR environment. It involved the end-to-end development of a new and novel system for data collection. The data collected was then evaluated using state-of-the-art emotion detection models. The novelty of this project lies in three key areas. Firstly, though there is a rapidly growing interest in the fields of both VR and music therapy individually in the mental health context, there is a lack of research into their combined effect in alleviating mood disorders. Second, previous studies focus on music therapy using only existing clips and not generated music. The use of existing music, which is user-selected, varies across participants and relies on user feedback to label the type of emotion it elicits. This can adversely affect the quality of the data. Lastly, though emotion classification using EEG is a rich field of scientific research, it is yet to explore the combined effect of VR and generated music on the patient's mood in terms of EEG signal analysis and classification. In this study, the participant's emotional state was quantified using a three-dimensional emotional model, the valence-arousal-dominance model. Specifically, we studied only the valence and arousal dimensions corresponding to the emotional spectrum highlighted in yellow on the left. Valence gives a measure of pleasantness, while arousal measures alertness. The music generated and used as stimuli in this experiment had a fixed valence value of 1 and changing arousal values of 0.1, 0.5 and 1 as shown, corresponding to the three categories of music stimuli presented in the sessions. For each participant, the flow of the data recording session was as shown. They were first asked to fill a pre-experiment survey to get a subjective gauge of how affected they actually are by music. Next, three blocks, block 1, 2 and 3 of active music stimuli were presented, each separated by rests and consisting of three sub-blocks. Each sub-block further contained alternating VR music stimuli and rest scenes. The participants were overall divided into two groups based on whether the high or low arousal stimuli were presented in the first block. Short samples of high, neutral and low arousal music generated using the system are as follows. The overall system was designed in such a way that it would be easy to modify and reuse. The music generated, as in these samples, was played and exported using an audio workstation Ableton. 20 such music clips were created for each category and randomly sampled for use in the experiment, as seen in the blue blocks of this diagram. As in the green blocks, the entire system was based in Unity, and the user interface and music stimuli were presented to the participant via the Oculus Quest 2 headset shown on the left. Regarding the purple blocks, the participants' EEG responses were recorded using the Muse 2 headset shown on the right. They were labeled using a mapping function. At the end of each data session, this function mapped the time series EEG data to the labels and timestamps collected by the Unity backend to produce a labeled EEG data file. This was later used to train the deep emotion detection models. A demo of the system during a session where a participant, the VR music stimuli and the EEG data streaming on the visualizer used is presented next. An example of the label time series EEG data from a participant after each session is shown on the right. The EEG data collected for each participant was then epoched. This involved extracting those parts of the EEG data corresponding to the active music blocks and discarding that in the rest periods. This extracted data was further segmented into 2-second intervals with a shift of 1 second and normalized to be used for model training. The state-of-the-art models TSception and EEGNet were trained using 3-fold cross-validation for both 2-class and 3-class classifications, which combined the low, neutral, and high arousal classes in all the possible ways as shown in the table. The data division during the 3-fold cross-validation to create the train, validation, and test sets is shown on the bottom right. We are happy to report that the models were able to distinguish between the emotional states in the EEG data. As can be seen, EEGNet outperformed TSception in 3 of the 4 classification strategies. However, their results were comparable. It was further verified that there was no significant difference in the results produced by these two models using a 2-sample t-test, which returned p-values greater than 0.05 for both low-high and low-high neutral classifications. The high classification accuracies of up to 83.44 for low-high classification show that the data collected contains distinct emotional arousal states elicited by the VR music stimuli in the different blocks of this experiment. An analysis was also carried out to determine whether the experiment protocol administered had any effect on the classification accuracies reported. For the HNL group, the first block of the experiment contained high arousal stimuli, followed by neutral and then by low arousal stimuli in blocks 2 and 3. LHN was the opposite. As seen, the accuracies were comparable, but HNL group's accuracies were slightly lower and had more fluctuations across participants as shown. A potential reason for this could be that more subjects in this group reported that they felt very sleepy towards the end of the experiment, as compared to the LNH group during the post-experiment survey. Lastly, a detailed analysis of the pre- and post-experiment surveys was carried out to see if there was a correlation between the reported accuracies and the participants' subjective responses. As seen here, the participants having the best accuracy gave much longer post-experiment feedback, and a larger percentage of them reported a change in mood, while only one felt very sleepy. On the other hand, participants having lower accuracies had much shorter feedback while reporting that on average they were less affected by the stimuli and sleepier after the experiment. To conclude, this project involved the end-to-end development of a novel system to study the combined effect of VR and music on emotional arousal states of participants. The dataset formed using this system was evaluated on 2 state-of-the-art models, producing high average accuracies across all participants, especially for low-high arousal classification, which reached 81.57% and 83.45% for TSception and EEGNet respectively. Based on this result, we observe a notable distinction in the participants' response to stimuli corresponding to different arousal states. The system developed, combining VR and generated music as stimuli, proved effective in classifying emotion using the resulting EEG data responses. Thus, it is a potential method for inducing intended emotional arousal states and thereby alleviating mood disorders via mood regulation, which can be further explored in clinical trials.